Hello everyone, welcome to the virtual lab class. So till now what we have seen is lab experiment in virtual lab for fluid flow operations. So first 1 to 6 lecture were based on the fluid flow operation laboratory experiments, right? And from the last lecture we started experiment on heat transfer laboratory, where we studied heat transfer by conduction in the last lecture. In today's lecture we will continue that analogy and then we will move forward with the heat transfer by convection. Next lecture will be on the radiation part, right? So let us begin with today's class. So aim of our experiment today is to understand heat transfer in convection, and then we will determine overall heat transfer coefficient for a given vertical metal cylinder surface through natural convection method, and we will determine the Nusselt number value for the given conditions, right? So again, like the previous experiment, it's fairly simple experiment, but we will try to understand the fundamentals behind the convection, various equations that are used to define the convection, and what output we will get through these experiments. So as we discussed in the previous class, that three basic mode of heat transfer are conduction, convection and radiation, right? In conduction, heat transfer is occurring because of molecule vibrations, right? This molecule vibration transfers the kinetic energy from one part to another part. So from higher temperature we will have higher oscillation, and at lower temperature we will have a lower oscillation. So kinetic energy will be transferred from this higher oscillation to the lower oscillation, and thus the energy will be transferred, right? In the convection, heat is transferred by collision or diffusion of molecules within each other, right? So this collision leads to the transfer of kinetic energy from one point to another point. Thus total energy is transferred, total heat is transferred. And for the radiation, what we learned that the both convection and conduction requires a media for the heat to flow, right? While radiation, heat is transferred through the electromagnetic waves, so we don't need any medium. It can pass through vacuum also. And the example that we studied, that most of the conduction occurs in the solids, right? So solids are the best example to show the conductive heat transfer, while for the convective heat transfer we can consider the example of fluid, be it be air flow, be it be fluid flow inside the pipeline, water flow in the cooling tower, fluid flow over any surface, right? While for the radiation, the best example is heat transfer from sun rays to the earth surface, right, which occurs via electromagnetic wave through vacuum. So we don't need any medium for heat transfer. Now when we talk about the convection, so in the convection, heat is transferred through the molecular movement of molecules, right, which are randomly distributed. So consider this confined space where we have some gas molecules. They are moving around in this box, right? And through this collision and diffusion, the heat is being transferred through them, right? Now depending upon the fluid motion that we have, we will have different sort of convective heat transfer. For that, let's look into the basic classification of convective heat transfer. So convective heat transfer is classified into two parts. One is natural convection and second is forced convection. So in natural convection, as its name says, that fluid motion is occurring naturally, which is due to the differences caused by the buoyancy forces and the density variation, right? So consider an example that we have learned in our 11th 12th science classes, right, that during the day air is flowing from the sea surface to the earth, right? So that's why we get a cold wind during the day from the sea surface to the earth. Why? Because during the day the air which is in contact with the earth's surface heats faster. Because of it, its density is lowered. Now this low density air will try to move upwards, while in contradictory the air which is in contact with the sea level, which is in contact with the water, will be heated at relatively lower rate. Because of it, it's highly dense zone, right? So because of that, what will happen, this high dense air will remain closer to the surface, while the lower density air will try to move up. So because of that, there is this pressure difference is being created. You have higher dense air on the sea level, lower density air on the surface, which will try to move up. Because of that, there is a vacuum which is being created, and that pressure difference causes the high density air to move from the surface to the earth, right? So this is the basic example of buoyancy forces and the density difference. So in natural convection, what happens, due to the density difference, the fluid which are being heated, so if we consider the example of a liquid, let's say this is the part of a moving fluid, right? So, and below is the, let's say there is this hot surface. So any fluid molecule which are closer to the surface will be heated much faster, right? So if we look at the local density of this part will be lower, since it's heated. So at a higher temperature, density will go down. So this molecule will tend to move upwards, right? But compared to that, the surface molecule which are at relatively lower temperature, I'm saying relatively lower temperature, not low temperature, okay? So these are at the lower temperature, so density in this upper region will be high. So because of that, they will tend to move downwards due to the gravitational force, right? So the difference in the buoyancy and the density results into the fluid motion in up and down direction. So that is this, because of which the heat is transferred from one place to another place. So that's why it's called natural convection, right? So example, we have seen that sea and land breeze, then condensation of water vapor, that is also an example of natural convection. While in the forced convection, the fluid motion over the surface or within the pipeline is due to any external sources, be it be pump, be it be stirring, be it be fans, right? So best example you can consider is our cooling tower, natural heat exchangers that we have. Even in the cooling tower are the combination of both natural as well as forced convection, though the forced convection plays a dominant role there, right? Now as a chemical engineer, we deal with both natural convection as well as forced convection, and in many real life application includes both the combination of forced plus natural convection. Sorry. So the cooling tower, as I said, is the best example you can consider. Now apart from this, so this is the classification based on the how fluid is flowing, how fluid motion is occurring. We can further differentiate them in terms of based on flow regime. So that we can divide it into laminar and turbulent convective heat transfer. So in the laminar convective heat transfer, as the name suggests, that the fluid flow will be laminar, right? So it will be in the laminar region. So you will have smooth boundary layers, right? Smooth and ordered boundary layers, because of which, since layers are arranged parallelly to each other in the laminar flow, one can think about that heat transfer is occurring from this layer to one layer to another layer. Thus you can consider heat transfer is occurring by conduction within the fluid layers, right? So you can visualize heat transfer by conduction within a fluid layers. While for the turbulent heat transfer, you will have chaotic, sorry, you will have chaotic motion of fluid with eddy currents, right? So because of that, because of this chaotic motion, this eddy formation within the fluid, there is mixing occurring between the fluid, right? So thus heat transfer is enhanced because of this mixing in the turbulent region. So heat transfer is enhanced because of internal mixing, you can say. So it's more convective, right? So that is the basic difference. If I want to differentiate the convective heat transfer based on the flow regime, so we can either differentiate into the laminar convective heat transfer or the turbulent convective heat transfer. Apart from that, if you want to account for the phase change also, that in that case, if we account for phase change during the convective heat transfer, so then we can classify it as a single phase, convective heat transfer, or double phase convective heat transfer. Now again, as its name says, you can directly draw the parallel from the name itself, that in the single phase convective heat transfer, no phase change will occur. So most of the heat exchanger equipments that you will see, the double pipe heat exchanger, plate and frame heat exchanger, so majority generally does not include the phase change. Obviously there are reboilers and condensers that include the phase change, but that will come into the double phase convective heat transfer. So common heat exchanger for a lower utility applications does not include any phase change, right? So the example could be cooling or heating of pipeline Generally, this includes that there is an outer layer of a jacket through which either a heating media or cooling media is passing in the pipeline, which maintains the temperature. Then, in the double phase convective heat transfer, phase change will occur. So, your boiling or condensation are the two common examples. So boiling, so you have boilers to generate a steam, you have reboilers at the bottom of the distillation column to provide an heat to the distillation column, then condensers to maintain the temperature of condensers to maintain the pressure of distillation column to condense down the top vapor product, right? Apart from that, to condense the hot vapor coming out of reactor, right? So there this condensation plays a role. So you have both, like fluid convective heat transfer is occurring through internal motion of fluid as well as the phase change. So phase change will include the latent heat also, right? So these are the some of the classifications of convective heat transfer. Though the major classification is this, that you differentiate the convective heat transfer in the natural convection and the forced convection. But apart from that, there are different angles from where we can look at the convective heat transfer. One is at which regime we are in, be it be laminar or turbulent, or whether there is a phase change occurring or not, right? Now there are various quantities to differentiate or quantify this convective heat transfer. We will come to that part also, but before that, let's understand how to quantify the convective heat transfer. So for the convection, Newton's law of cooling is used, which says that the rate of heat loss for any body is proportional to the difference in the temperature between the body and its surrounding, right? So if you have a hot ball at a temperature capital T and its surrounding is at a smaller temperature, right, then heat transfer from this body to the fluid or surrounding air will be proportional to the temperature difference, right? And if you remove the proportionality, then you can add the constant, right? So this is obviously area to account for the rate, so flux is converted to the rate, while H is your heat transfer coefficient, and its unit is watt per meter square Kelvin, right? Now the heat transfer coefficient is a kind of a fluid property, right? So it will change according to the fluid flow conditions as well as what kind of fluid we have in our system, right? Now let's try to draw a parallel between the conductive and convective heat transfer. So one can consider that convection is enhanced form of conduction. The movement of fluid surrounding the metal helps to carry the heat transfer by conduction. So what does this line want to say? So let us consider that I am thinking about fluid motion through a pipeline. So this which is surrounded by another fluid. So let's say there is this cold fluid moving inside, and then you have hot fluid outside. So heat will be transferred from outside outer fluid to inside fluid, right? So for that, how this heat transfer will work, that now let's look at the cross section here. So if I look at here, you have this metal surface, the pipe surface, right, with some thickness. Hot fluid is outside. So here, this is hot fluid. Convective heat transfer will transfer heat within the fluid. Now from fluid to surface, from this point to this point, conductive heat transfer will happen, right, which will increase the temperature at the inner wall of your tube. Then from this inner wall, you will have another point within the fluid where further heat transfer will happen, which will be via convection. So you have convection here from this point 1 to point 2 convection, point 2 to point 3 conduction, point 3 to point 4 convection, right? Now if the movement of fluid surrounding the metal helps to carry the heat transfer by conduction, so let's say if we increase the more turbulence in the outside fluid or the inside fluid, then heat transfer from point 1 to 2 and 3 to 4 will increase. So let's say heat transfer from point 1 to 2 is increased. Because of that, temperature at point number 2 will increase, which will create a higher temperature gradient between point 2 to point 3, which will further enhance the conductive heat transfer from point 2 to point 3. And similarly, if there is inside turbulence also, then heat transfer from point 3 to point 4 will further increase, right? So convection in a way is an enhanced form of conduction where both help each other. So if you want to draw a parallel, we can compare the heat transfer by conduction and convection. So there is this heat transfer which is occurring from point 1 to point 2, point 2 to point 3. Okay, now that will be constant for both convective and conductive heat transfer. So if I compare it, we can write for the convective heat transfer, we have an equation Q is equal to HA delta T. Conductive, we have the equation that we derived last time, that was Ka delta T by delta X, right? Now for a moment, see here the area is constant. Let's consider temperature difference is also same. Then we will get that heat transfer coefficient is thermal conductivity divided by delta X, or you can replace this delta X with L, where L becomes your characteristic length, which depends upon the geometry of your system. So this relates conductive and convective heat transfer, where the heat transfer coefficient of a given fluid can be computed by its thermal conductivity divided by the characteristic length of the geometry that it's flowing over, right? So in fact, as the temperature of cylinder increases, fluid motion increases and becomes more turbulent, whereupon the fluid becomes more efficient at carrying heat, and H can turn up to 10 to the power 2 to 10 to the power 4 times higher than K by L. So if we will have more turbulence, then the heat transfer coefficient will dominate over the over the thermal conductivity. So convective heat transfer coefficient will dominate over conduction. So if you want to quantify it, this dimensionless quantity, which is known as the Nusselt number, is used when Nusselt number gives you the ratio of heat transfer by convection to conduction, and it is given as heat transfer coefficient into characteristic length divided by the thermal conductivity, right? So this Nusselt number helps us to identify which mode of heat transfer will be dominant, be it be convection or be it be conduction. There are some reference, I will go to this reference after the explanation part. So how this quantity is useful, how do I knowing Nusselt number help us, right? So one of our aim is to determine the Nusselt number here also. So for that, let's consider different quantities that are being used to quantify both convection and conduction, right? So there are this dimensionless number which are used to quantify convective heat transfer. Okay, so let's go by I will name some of them and their purpose. So first one is Grashof number, GR. You must have studied this dimensionless number in your heat transfer course, right? So I am not going into their equation or derivation part, but rather what they actually mean. I think it is double F probably. So first is Grashof number, which is used for a natural convection. Okay, so used in natural convection. So this quantifies the natural convection part, where one can consider it is as an analogous to Reynolds number. So it gives you the ratio of buoyancy to the viscous force. buoyancy to viscous force. Similar analogy in the force convection is the Reynolds number. So if you have higher Grashof number, that means you are in a turbulent region. If you have a lower Grashof number, that means we are closer to the laminar region. There are equations for this also. I will show you it in the after this explanation part. Okay, so this Grashof number helps us to determine in which region we are lying. Then second number, that is known as the Prandtl number. Now Prandtl number is kind of it relates the kinetic viscosity to the thermal diffusivity. So it's a ratio of kinetic viscosity to diffusivity. So it helps us to relate whether the velocity boundary layer or the thermal boundary layer, which one be more dominant. So relates, or you can say compare the thermal and velocity boundary layers. So if Prandtl number is greater than 1, this shows that the velocity layer is bigger than the thermal layer. Okay, so the fluid motion will be dominant compared to the thermal diffusion, right? So if the Prandtl number is less than 1, that means that thermal boundary layer is more important, which will be heat transfer controlling step. Now the next dimensionless number, which is used to quantify the natural convection, is Rayleigh's number. So which is given as the product of Grashof number into the Prandtl's number. So this denotes, the Rayleigh's number shows us the onset of turbulence in the natural convection itself. So there is this quantity, like if Rayleigh's number, probably people relate to 10 to the power 8 to or 10 to the power 9. So if it's greater than that, then we are in a turbulent region. If it's less than that, then we are in the laminar region. So then this further Rayleigh's number is related to the Nusselt number, to which I will come in a minute. So this quantities were for the natural convection. This 1, 2, 3. In the natural convection, not exactly, I think Prandtl number is used in both, so let me change that. So Grashof number and Rayleigh's number are mainly used to quantify the natural convection, while Prandtl number is used for both natural and the forced convection. So another quantity which is being used for forced convection is Reynolds number. We already know this, right? So that is inertia force by viscous force. We have already used this Reynolds number in our fluid flow operation laboratory, so I am not going into details. Then after that you have a Nusselt number, which we learned is ratio of convective heat transfer to the conductive heat transfer, right? So this helps us to determine which will be more dominant? Higher Nusselt number denotes that convection will be dominant, okay. So yeah, these are the quantities which are used to differentiate the convective heat transfer in the natural and the forced convection. But how it is useful to us, right? That is our main purpose. Like why we need to find the Nusselt number for the fluid, or Grashof number, or the Rayleigh number. How it will help us as a chemical engineer. So for that is that usefulness of dimensionless number. So that is, consider an example. If we know Nusselt number and the thermal conductivity of our fluid, then we can compute heat transfer coefficient from the Nusselt number equation, which is Nu is equal to Hd by K, right? So we can compute the H. Once we know the heat transfer coefficient, then we can find the heat transfer by convection, which is Q is equal to Ha delta T, right? So if I know the Nusselt number, then I can find the heat transfer coefficient. If I know the Nusselt number and the conductivity, I can find out the heat transfer coefficient. Now we know that the thermal conductivity is a fluid property. It varies with the temperature, but let's say there are empirical equations available for finding the thermal conductivity with the temperature range, right? So if we know that equation, we can find out the thermal conductivity of a given fluid. And somehow I have a Nusselt number. Then as I said that the heat transfer coefficient is a fluid property. So it will change with the type of fluid that we have. And its flow condition also. So it's difficult to determine heat transfer coefficient at every point through the experiment. Obviously we will be doing experiment right now to determine the heat transfer coefficient, but for all condition, for all types of fluid, it's difficult to determine heat transfer coefficient for that particular condition. Rather we will need some sort of a empirical equation to formulate, to compute the heat transfer coefficient, right? So we said, okay, if we know the Nu, if you know the Nusselt number and we know the thermal conductivity, we can compute the H, right? So this H, heat transfer coefficient value, is important for our heat exchanger design. Apart from that, your even cooling tower and the pipeline heat tracing or cooling lines, they all are evaluated based on this heat transfer coefficient of the fluid, right? So it's an important quantity. Now there are multiple empirical equations. Available which provide Nusselt number for natural as well as forced convection. So some of this equation you have already heard or seen in your heat transfer classes. So for forced convection, one equation is your Dittus-Bolt equation, which kind of gives you that which relates Nusselt number to your fluid flow condition, which is Reynolds number and the Prandtl number, right? Where this N can be 0.3 or 0.4 depending upon heating or cooling part. Then, so this Ditter's bolt is used for turbulent condition, turbulent flow. And then for the laminar flow of a fluid through a pipeline, there is this Sider-Tate equation, right, which is used for laminar flow, where Nusselt number is 1.86 times, Reynolds number is to 1 by 3, Prandtl numbers to the power 1 by 3. Okay, so this was that in the force convection we related Nusselt number as a function of Reynolds number and the Prandtl's number, right? Now there are further modifications to this equation to incorporate the change in the viscosity, change in the thermal conductivity effect, right? So again I will show you that equation part. If we are in the natural convection, then Nusselt number is related to the Rayleigh number, right? So it's shown as some empirical form of the Rayleigh number. So the both Reynolds number, Prandtl's number or Rayleigh number in the natural convection are the fluid property. So they depend on the fluid flow condition. Okay, so if you will see the equation of this dimensionless quantity, they are fluid flow dependent quantities. Okay, so either it will depend on the fluid property or the fluid flow conditions. Once we know that, then we can use this empirical equation to relate and find the Nusselt number for our condition, and from that we can compute the heat transfer coefficient and back calculate the total heat that will flow due to the convective heat transfer, which is our ultimate goal, right? So again I will come to this heat exchanger example. So in this heat exchanger example, as we saw in the last time also, that we have to find both the internal and inside heat transfer coefficient and outside heat transfer coefficient, right? So this inside heat transfer coefficient is heat transfer coefficient of the fluid which is inside, outside will be on the fluid for the which is outside on the cell side, right? So we know the flow conditions, flow rate that we will put a fluid through the heat exchanger. So we know the flow condition, then we can compute the Reynolds number, we know the temperature pressure condition of the cell and tube, right? So we can compute the Prandtl's number, etc. Then we can use this empirical correlation to find the heat transfer coefficient and then do the designing of this heat exchanger. So this is the overall picture of finding the heat transfer coefficient or relating the Nusselt number to the heat transfer coefficient. So what we will do in this experiment is that we will do a convective heat transfer in a natural convection experiment. Then we will find the heat transfer coefficient at different pipe length, find the Nusselt number corresponding to that equation, corresponding to that experiment. Okay, so what I will do is, before moving to the experimental part, I would first like to show you the various equations that are being used to quantify this dimensionless number, right? So let me share my screen here and I can stop presenting. Okay, yeah. So here if you will see, I have provided some reference for the Nusselt number. Obviously, I would suggest to use the book reference rather than the Wikipedia references. Okay, but here you see the definition of Nusselt number, then how it is quantified, its derivation, and here are the empirical correlation. So as I said that for the natural convection, Nusselt number can be expressed as a function of Rayleigh number and the Prandtl number, right? For the forced convection, Rayleigh number will be replaced with the Reynolds number right? So for a free convection, you can see there are various equations. For a fluid flow from a vertical wall, this is how you compute the Nusselt number. Free convection from an enclosed surface, you compute it this way. For a flat plate laminar flow, for a flat forced convection in turbulent pipeline. So this was for the till this point it's for natural convection. Now if we are moving into the forced convection, so depending upon the laminar and the turbulent flow regime, we use different equations, right? So these are the all correlations available. We already discussed the Dittus-Boelter equation, right? So these equations are useful to compute the Nusselt number and thereby computing the heat transfer coefficient. Here you can also see the further definition of other dimensionless number. So let's say if you want to see what is the Rayleigh's number, go to its reference and check it out. There are equations provided. I haven't gone into the equation part here, but you can see if you want to see what is the Grashof number and its equation, you will find it here. Okay, so this equation part is not important for us as of now, so that's why I have not gone into the details of that, but you can definitely check it out. So there are various correlations available to understand the convective heat transfer. So that was one part. Now let's move to the experimental part today. So first, let's look at the real world example of this experiment, and then we will move forward with the virtual lab part.
Heat transfer by convection. Aim: to determine the overall heat transfer coefficient at the surface of the given vertical cylinder by natural convection method and the value of Nusselt number in each case. Apparatus: natural convection apparatus. It consists of a tube fitted vertically in a rectangular duct which is open at the top and the bottom. An electric heater is provided in the vertical tube that heats the tube surface. Heat is lost from the tube to the surrounding air by natural convection. Air around the tube gets heated and becomes less dense, causing it to rise. This in turn allows the continuous flow of air upward in the duct. The temperature at various locations on the surface of the vertical tube is measured using thermocouples. Theory: heat transfer is the energy transfer that takes place between material bodies as a result of temperature difference. The rate of heat transfer Q by T at which a hot object transfers heat to surrounding fluids by convection is approximately proportional to the area A of the object in contact with it and the temperature difference delta T between them. Newton's law of cooling expresses the overall effect of convection by Q by T is equal to VI is equal to HA delta T, where Q by T is the rate of heat transfer, V is the voltage given to heater, I is the corresponding current, A is the area of the given vertical cylinder, delta T is the temperature difference between the surface of the cylinder and the surroundings, and H is the convection heat transfer coefficient. H depends on the shape and the orientation of the object. It is used as a factor for calculating heat transfer between a fluid and a solid, between fluids separated by solids and between solids. From the value of H, we can also determine Nusselt number N, which is M is equal to HL by K, where K is the thermal conductivity of air, L is the characteristic length of the cylinder. Procedure: power on the switch. Using the white knob on the apparatus, we can fix the voltage and the corresponding current. When the steady state is reached, The temperatures T1, T2, T3, T4, T5 and T6 of the thermocouple on the surface of the given vertical cylinder are noted. The experiment is repeated for different values of voltage and the corresponding current. Applications. The principle of heat transfer by convection has been used in wide variety of areas like cooling of transformers and rectifiers, heating of houses by steam or electrical radiations, cooling of electronic devices like chips, transistors by filled heat sinks, cooling of reactor core in nuclear power plants, and so on.
So this was the the actual experiment part. So it's again fairly simple experimental setup compared to the previous experiment that we have done. So let's go to the experiment. So it's in here, heat transfer by conduction, convection and radiation. So go to the heat transfer by natural convection experiment. Here you will see some theory related to the experimental setup. So as it was described in the video, that we have this wooden box material inside which the cylindrical tube is placed, which is heated through a heater, and the air flows from bottom to top through the natural convection, which takes the heat from the hot surface. Air is heated and it's going outside, right? So this is the natural convection. Now the below air is at a lower temperature, so has a higher density. The top air, which is in contact with the surface, will be heated, so it will have a lower density, so it will try to move upwards. Because of that, there will be negative pressure gradient created here, which will cause the bottom air to move further up, and thus the natural convection circulation will begin. Okay, so same theory has been discussed here. The procedure for the experiment is given. So what we will do, T2 to T5 temperature, T2 to T5 are the metal temperature, so which will give us the hot surface temperature. So average of these four temperature will give us the hot surface temperature. T1 and T6 are the entry and exit point temperature of the airflow. So average of this will give us the overall temperature of surrounding air, surrounding fluid, right? So to compute that, we will compute that total heat transfer will be given by voltage into a meter reading, right? So that will be our total heat transfer. Area will be area of the surface over which the fluid is passing. So it's a cylindrical surface, so it's pi dl. Then the heat transfer coefficient will be Q divided by A into delta T. And then Nusselt number will be calculated as H into L by K. Right? So here one thing that we will need is a thermal conductivity of our fluid. So for air, the thermal conductivity is given as 0.024 watt per meter Kelvin. So let's move to the experimental simulator. Once you will load the simulator, you can see the similar setup what was shown in the experiment. Here you can select various materials for your cylinder, right? Remember, here we are computing the property of air. Here we are computing the heat transfer coefficient of the air. So the choosing this material will not have much influence on the heat transfer coefficient because it's air property and it's okay. But this will have a effect on how faster your equilibrium is being achieved, right? So let's say some of this material will have higher thermal conductivity, because of which surface temperature will be higher. So there will be slight difference in the regime that you are in this natural convection. So because of that, it will have some influence on the natural convection part, but that margin might not vary too much, considering here all of the materials are from a metal surface, right? You can select the dimension of wooden box. So this is the wooden box inside which the cylinder is placed, right? You can change the diameter of cylinder, length of the cylinder, right? So change this slider and it will change the values accordingly. Thickness of the cylinder. If you will do this, it will show you the cross sectional part. So let's say we select this. Here we have selected aluminum and I'm keeping the default value. And as you do the power on, you can see the experiment has started. Now we have to wait. Sorry, one thing I forgot. I haven't changed the heater temperature. We haven't turned on the heater. So this knob, if you will rotate it, it will change the heater to a, it will turn on the heater. So let's reset again and turn on the heater to some higher value and power on the experiment. So initially you cannot directly take the reading, since this measurement techniques are working at a steady state. The last experiment that we did for the heat transfer in conduction, there we were computing the thermal conductivity and it was steady state method, the hot plate method, right? So for that we have to wait for some time for a steady state to attain. When we will know that steady state is being attained once the temperature fluctuation from T1 to T6 will be negligible, then we can say okay, steady state is attained. So here after 20 minutes you can see this temperature are not varying. They will vary but the quantity will be in the decimal. Okay, so then you can say okay, now steady state is being attained. Now I can take the temperature readings, right? You take the corresponding temperature reading, you note down the voltage meter and ammeter reading, right? And then put it in your table and compute the heat transfer coefficient and the corresponding Nusselt number. So let's look at the preloaded examples that I have. Here, so material that I have selected was iron, and this were the materials property, thermal conductivity of air, area is pi dl, and I have converted it to meter square. We know the voltage and current reading, we noted down the temperature reading. So average temperature will be average of T2 to T5 temperature, that will be hot surface temperature, and the average air temperature will be average of T1 and T6. Then heat transfer is given by voltage into current. So this much watt heat is transferred. So thermal conductivity is Q divided by area divided by delta T. So this is the thermal conductivity that we are getting, and the corresponding Nusselt number. So Nusselt number is H into L by K, right? So this is the thermal conductivity H, sorry, not thermal conductivity, heat transfer coefficient, my mistake. Then Nusselt number is H into L by K. K value is given, that thermal conductivity of air is 0.024, right? So thus we compute the Nusselt number. So at a higher voltage you can see, because of the increase in the temperature, there will be turbulence in the fluid surrounding it. So there is this change in the Nusselt number value also, right? Now Nusselt number gives us the ratio of convective to conductive heat transfer. So here at a higher heating rate, Nusselt number is decreasing. This shows that at a higher heating rate, conduction will be dominant compared to the convection part. Okay, since it's a natural convection, so heat transferred by the convection won't be that significant compared to the conduction, since the surface temperature, you can see here, it's much higher, 120, 126, 130. So from the surface to the fluid layer, the conductive heat transfer will be dominant, right? Because of that, Nusselt number is low. You can do same experiment with same dimensions for the other material, and you will see there is not much difference in the thermal conductivity, not thermal conductivity, sorry, heat transfer coefficient value, right? Since I said that it's a fluid property and it's a convective fluid, so this material should not affect it too much unless the thermal conductivity of the cylinder is so low that it changes this T2 to T5 temperature significantly. In that case, you will notice the difference in the heat transfer coefficient. Now let us consider the same material. So here I have selected the material iron, but this time we have changed the length of the cylinder. So length of the cylinder is increased from 55 to 60, and at the same voltage and current reading we are computing the heat transfer coefficient and Nusselt number. So you can see this 3 value. So since I changed the dimension, heat transfer coefficient has changed while the Nusselt number remains same. But if I don't change the length and increase the diameter, so here the diameter has been further increased from 7 to 10. In that case, you can see that the both heat transfer coefficient and the Nusselt number both has changed. Now since the length is more, the area for the conductive heat transfer has also increased. Because of that, the Nusselt number has gone down. So this shows that at a higher area, you can visualize it in that sense, right? If the diameter is higher, then pi dl, area is also higher, so conductive heat transfer will also increase. So because of that, Nusselt number is low at the same heating rate, right? So this is how you can compare various results, right? So what you can do is you can repeat this experiment for various material to see whether the material property has some effect on the heat transfer coefficient. Apart from that, take various dimensions and repeat the experiment, compute the heat transfer coefficient. You can also try to correlate the empirical equation of Nusselt number, right? So for a natural convection, Nusselt number is related to the Rayleigh number. So you can compute the Rayleigh number and then see whether that empirical correlation is being followed or not. So this was the part for heat transfer through the natural convection. So in this experiment, what we did, we learned about the convection principles, classification of convection. So primary classification is natural and the forced convection, and then based on the flow regime we can also further divide into the laminar convective heat transfer, turbulent convective heat transfer, or whether phase change has occurred or not. We learned about the Newton's law of cooling, which is very straightforward. Try to relate the convection and conduction and use of various dimensionless number to find the heat transfer coefficient in the convective heat transfer, which is ultimately used for the design calculations of various equipment as a chemical engineer, right? So this was your experiment for today's class. For the next lecture, what we will do, we will move forward with the last mode of heat transfer, which is radiation. We will verify the heat transfer equation for the radiation part, right? And then further we will move forward with the mass transfer laboratory. So this was it from my end. Now if you have any doubt, we can discuss it out. I'm going to stop this recording and then we can discuss it.